Okay, so question one here was, I guess this is the last week we had a question where we were trying to sort of improve on export and commit by turning it into an anytime algorithm instead of the original fixed time version. And then we pointed out another sort of shortcoming of it, which is that the expiration time in our original discussion depended on the suboptimality gap. So question one here was looking into how we can remove that dependence, I guess, at the cost of a so worse regret bound. So I guess the question was something like, show that we can choose them independently of delta in the case of just two arms where there's only one gap, such that the regret of export and commit with expiration time m on any bandit is bounded by export and commit. It's bounded by the suboptimality gap of that eta plus some constant times 1 over cube root of t. So instead of a square root of t bandwidth, we downgrade to a cube root of t. Decreases lower, but we get this for we get this independence of the gap in the choice of m. I guess this was part A. And yeah, we can come back to part B. I was going to ask Jean-Marie if he could walk us through your solution.
Sure. So my solution is not absolutely complete. I was a bit lazy, so I just assumed I could take m equal t power 2/3, and so I didn't deal with the rounding to an integer, which would, yeah. So it's not quite complete.
It should be like something like the ceiling of that maybe, but I think in the up to that approximation error we can just assume
yes.
assume it's
So I think if you want to be complete, probably you want to round down, but I'm not completely sure.
I mean, I would imagine either one
I
works.
didn't do it anyway, so I will not.
Okay.
Yes.
Well, yeah, we can just
So
work with this.
Let's just assume t, is a cube. So from the notes of week 3, lemma 10, we have an expression of the regret of ETCM in two terms, which is basically that the regret at time t of ETCM is equal to 1 over t m times delta. So since we only have two arms, we just have one delta plus yes, plus t minus ma, and yeah, so the times delta times the probability that we didn't choose the best arm after the exploration phase. And then I guess everything over t. And also for the first term in the summand.
You got it right. Is it bound in the total regret?
Yeah, that's fine too. So this way you don't divide by t. Yes, and then so if we substitute our choice of m, so t to the 2/3, we can do it very simply for the first term, and yeah, what I did for the second term is that basically I forgot about the minus 2m, and I just had the t remain alone to simplify things.
So in the case we just get,
so you lose a little bit, but it's not horrible. Yes, and then you need to find some expression for p of choosing the wrong arm.
And we had a bound for this using the Chernow bound.
Yes, exactly. That's what I did. And so what I had was e to the power minus t to the 2/3 times delta squared over 4. And basically you obtain this by working with one Gaussian distribution and using the Chernow bound. Well, basically what you want to do is you get m tests of both arms. And so the value that you get for each arm is one Gaussian. And when you sum different arms which have independent probability, the sigma Gaussianity, so the sigma in the sigma Gaussianity, it just adds when you add sigma sub-Gaussian variables. Because basically it behaves like a variance for a Gaussian variable. That's kind of the heuristic for that. And what you want to do is you want to see if the best arm, the average of the test for the best arm minus the average of the test for the worst arm is likely to have the wrong sign. So to have the sign which is opposite to its expectation. And you bound this with a Chernow bound, and you can directly use a Chernow bound and you get this expression.
Right.
Yes.
And
yes. And what we want to do now is to look at this last term and see what is the worst case in the choice of delta for this last term. And so basically we maximize this term for t fixed, but for variable delta.
So we look at the maximum over delta. Right, and then
yes, and basically you can take the derivative and maximize this by looking at where the derivative is 0. And you get two extremums. One is a minimum and one is a maximum, because like it's an odd function.
hmm.
And yeah, and you have only two zeros. So
Right, so if you
one
wanted to
is
understand
a
this,
maximum and the other is a minimum.
so delta is always positive, so we really only, or non-negative, so we only care about this in the
Yes.
0 infinity. And I guess on this interval, this function probably looks something like this, right? Where at 0, it's 0.
Yeah, it's better to
And it has
just
a,
have delta be positive, and then we don't have to bother about the 0. But
I mean, it could be 0, right? Because the two arms could be
yes, that's true. It could
equal.
be.
But then,
But when delta is 0, the regret is always null, so it's fine.
yes. So this function overall has this kind of shape, and then we can find the maximum by taking the derivative with respect to delta.
Yes.
And what is this spec? Did I get this right?
Yes, I
I
think
think
so.
shouldn't you have differentiated delta? Shouldn't it be like two delta or something?
Yeah,
The
I
2
think
was cancelled with a 4.
it was
Yes, so-
cancelled with the 4, and then we get a delta squared
so
from the.
yeah, but you are scoring delta in the second term, so I think you shouldn't, because it's cancelled with.
No,
over
because
four.
you have the delta remaining from
There's a
the 1.
delta the first term too.
Oh, okay.
So it's delta times the derivative of the exponential. So you get back the square again. Yes, and so this simplifies to delta squared times, yeah, exactly.
Right, so that means going back here, this means the maximum is equal to the value at this point.
Yes,
1/2.
exactly. Yes, that's exactly what I got. And so we can substitute back in the other formula, and we get the result that was
Here.
that we were looking
And-
for.
Right, and I guess we took if we take m equals t to the 2/3, this becomes
Square root of 2 divided by the cubic root of t.
yeah, and then if we plug this back in, then back in here, then we get this is less or equal to t to the 2/3 times delta plus its constancy. Okay. It looks good. Any questions from anyone about?
So I'm not sure what is the most elegant way of doing the rounding to the next integer or to one integer before, or exactly what's the proper way of doing that. So
Yeah, that is a good question. I mean, here if we take the,
I did look at it.
yeah, I guess it's a little tricky because in the second term we have the m in the denominator, while here we had the m in the denominator, so they kind of, we cannot round in the same direction and expect this to always work out. But I think,
Yeah, and we don't
if
have
I
a
rem-
constant in the first term. So
Yeah.
probably we should take the rounding down, but I'm not sure.
Yeah, I wrote up a solution that uses the floor of t to the 2/3. So the
Mhm.
first term, the explore phase, has the exact same inequality, but then in the second phase, we do have to treat the error by taking a floor, but it turns out to give a pretty small constant factor.
Yeah,
Like the
exactly.
optimal.
That was the proper way of doing it. I
Yeah,
think.
the optimal x is still square root of 2 over m, and then the expression becomes slightly larger, and we can divide this imperfect term by the perfect term and bound it by a constant.
Nice.
But if you do the floor, then don't you have to also have a max so that it's always at least 1?
Yes, I'm thinking maybe we could actually just take the ceiling
Oh, no.
and then put like a +1 here. And that way, and then this one, the other term is actually a.
I guess t can never be less than 1. As long as t is 1.
Yeah, you can always treat the situation for a small t separately anyway.
Yeah.
But it's kind of annoying to have a ceiling because then your first term is not what you want. And
But it is upper bounded by t to the 2/3 +1.
yes.
And then for the.
Yeah, and you can just
for,
add a 1 on the other side and it compensates, I guess, yeah.
Yeah, right. Yes. And so again, put a +1 here, and then for the other term we're fine because it's there we were overestimating by having m in the denominator. So it's
Yeah,
probably
that
one way
might
to
even
do
be
it.
simpler, yes.
Yeah, so there's a couple of ways to deal with the rounding. Any other questions?
So it's
And,
interesting why this function has a maximum. I didn't realize for ages that this function had a maximum. I was like thinking through logically, like, okay, what is this term? And basically, I mean, you probably all know, but when you have like a very small gap, you know, when the gap is 0, then the regret is 0. And when the gap becomes very large, then it becomes very easy to distinguish the two arms. So the gap, the regret also goes to 0 in that case. And I was like turning this over in my head, being like, wait, which way does this function go? Is it going up or going down? I was like, oh, it has a maximum. It's very interesting.
Right. Yeah, I think I gave this as a hint in the last discussion someone asked, and then yeah, I guess one way to suspect that it has a maximum is to, as Koshin notice that this is 0 when delta is 0, and also goes to 0 as delta goes to infinity. So, and it's always positive, so somewhere in between you would expect it would have a.
Yes, that's how I was also thinking about it for the second term. Is a cubic root the best result when you don't want to have an algorithm that knows delta in advance?
No, you can you can still do. So UCB still still has a square root, and that one works without
Okay.
knowing delta in advance, I think. So yeah, you don't. Yeah, I think you can. Yeah, you don't need to have a cubic root, but I guess for ETC, this is just the simplest way to fix it, but that one has the cost of
Mhm.
having a worse regret.
Okay, nice. Thank you.
Actually, could you also walk us through the second part?
Absolutely, yes. So for the lower bound, let me maybe start by stating the exercise. We want to show that the regret, well, we want to show that it's impossible that the regret is always smaller than delta over t plus a constant over the cubic root of t in the same setting. So with one sub-Gaussian bandit, but arbitrary expectations of the two arms. And so yeah, so let's assume that we have a policy for which we have a C which holds for all t and for all delta. And then we can think in the following way. So if for some t, pi chooses m larger than 1, then we will have a problem if delta is very large. And more precisely, we can take delta larger than tc over square over cubic root of t.
C over cube. So it's like C times t to the 2/3.
Yes. And yes, the reason is simple because the first term comes from exploration and the second term comes from exploitation. And if you explore for more than one round, then you will not get the term delta over t because you can just take delta huge and delta over t will dominate.
Right, so we had the regret is equal to like.
And so we can do a computation for that. So m delta over t is larger than 2 delta over t because m is at least 2 if it's larger than 1. And this is equal to delta over t plus delta over t. And then delta over t can be replaced by tc over over square root of t. So the two t's simplify and we have something which is strictly larger. Actually, because we choose delta to be strictly larger. Yes. And so that's what we get when we have m to be at some point larger than 1.
Mm-hmm.
And so we conclude that m must be equal to 1 or smaller for all t. But now we do the opposite. So we take delta constant and we take t very large. And we again have a problem because since the exploration phase has a constant size, the probability of choosing the wrong arm does not go to 0. and the regret should go to 0 when t gets large, because you have denominators in t for both terms. And yeah, that cannot work.
See. Right, and then
I think we should use a separate symbol from C.
yeah, maybe call it P. Yes, this is Alright, so this is like
Yeah, I mean, we can use this formula,
Yeah.
but like
Yeah.
just thinking heuristically, you know.
yeah.
I mean,
So
I think
if you take
one
the
thing
limit,
is
limit as
accurate
t
to
goes
just
to
say if, yeah, the exploration phase takes a larger and larger proportion of the number of rounds, and it has a probability which is bounded away from 0. So it goes to p, and yeah, it's larger than 0.
right. Yeah, so for if you only explore like once, there's a positive probability of picking the wrong arm, and then we accumulate constant regret at each round for those. The average regret in the limit is just bounded below by the probability of picking the wrong arm. Right? Does that make sense to you? So basically the idea here is that if you explore at least twice, which you would expect for a learning algorithm to explore some decent amount of time, then for large delta we get this bound, which shows that we cannot have a regret bound of this form. And if you don't explore enough, we only explore once, then we also cannot have a bounded regret going to 0, because there's a positive chance of picking the wrong arm. Any questions?
This is very helpful. Very helpful to see this. Thank you.
All right. Thank you, Jean-Marie, for walking us through.
Thank you.
Maybe can move on to question 2. So in question 2, we're looking at MDPs, and we talked about the diameter of an MDP, which is talking about the maximum expected time it can take to go between two of the states. And then in this question, we're trying to show that the diameter is finite if and only if the MDP itself is strongly connected as like a directed graph. I was going to ask if Joshua could walk us through a solution.
Sure.
Let me just unmute. Okay. So one of these directions is pretty straightforward. Like if the NDP is not strongly connected, then there's some starting state SA and some end state SB where there's no path between those. And then there's no policy that can find a path from SA to SB. And then we have infinite expected times of arrival between those two.
The notation. What was the notation for arrival time?
It's like TSB given S0 equals delta SA.
Right, so this is arrival time to SB is given that we start at the state SA. This must be infinite because there's just no way to arrive at SB at all if you start at SA, because there's no positive probability path in the graph.
Yep. And then for the other direction, if the MDP is strongly connected, then for every starting state and end state, we have such a path. And specifically a path of like state action to from SA to like going through some states to SB some action. Yeah. And we have the same thing for all other states, or going from all other states to the end state. Yeah.
Similarly for all states.
Yeah. And then we can consider the policy that goes from the start state through those actions until it either arrives at the end state or gets put on some other state that isn't on the path that it was trying to get through. And then
so something like take action AI in the sequence if
SI is
if we're at the right state along the path, and otherwise
take the state that you're now on, that you got put on, that isn't on the path, as your new starting state.
Try to take a path to B.
Yeah, and follow that path until you either get to the goal or get put away from the path again.
And I guess we need to fix these set of paths in advance.
Yeah, that's what the definition, like the definition says that there's for each such path of starting state and end state, there is a path. And so we take exactly the path that is given by that definition. But yeah.
And do we need to say the minimum length of such path, or does any length work?
Yeah, so now we can say that for each such path we have the time that path would take if it was successful, and we have the probability that that path succeeds, where the probability is just the product of all the probabilities of each of the steps along the path. So it's like the product starting from t0 to or t equals 0 to something like t0 minus 1 of the probability of tau of st and at of st minus 1, t plus 1. So it's just the transition probability from state st to state st plus 1. Yeah.
So this is for the, I guess, for this path between the.
Yeah. And we can say that time of that path is, in this case, just k. And then we can look at all of these paths, going from all of the non-end states to that end state, and take the minimum probability and the maximum time, and call those like p min and t max.
Something like this.
Yeah, now our policy just tries to get to the end path and has at least a minimum, at least a probability of p min to succeed, and that takes at most t max time, and we repeat that until we get there. So we can bound the expectation of the time of arrival by just like I guess the sum of like the sum over the amounts of tries it takes us.
Sorry, so say it again.
Yeah, so we have at least that, and yeah, and now we can bound the expectation of time of arrival. Yeah. By the sum over the amounts of tries it takes us to get to the goal. And that's like just from 1 to infinity. The p min for the try we're currently on times 1 minus p min to the power of n minus 1 times the time times n. So like n times the time is the the time, the maximum time is the time we at most take if we get there on try n. And yeah, that's, I don't know, I think I just had that cached. I don't currently know how to prove the conversion, but it's like geometric sum. It's just the time over, like, or the, if we take out the ty max, then all of this just comes down to 1 over p min. Yeah. And that's less than infinity, and we can do that for all of the possible endpoints of the path. And because we now have an example policy that gets the that gives us a bound for the argmin over policies, and yeah, then diameter is less than infinity.
I think the n in the exponent should be n minus 1.
Oh yeah, you're right.
Yeah. Okay. Yeah, that sounds pretty good. So basically, so the idea is, maybe I can draw a picture to help clarify. So let's say we start here and try to end here. And from the graph, we know that there's a path. S1, S2, and so on up to here, where if this is positive probability transition if we take action A1, take action A2, and so on, AK. And then basically we have such a path for each other state. So let's say there's a x tilde here. We also have a path, which might at some point intersect the other path. Doesn't really matter. And then basically the policy is, start at X, take action A1. If we end up at state S1, then all well and good. We take action A2. If we end up at S2, all well and good. If we don't, let's say we end up at X tilde somewhere else. If we get off of our prescribed path, then start following the path for X tilde, which is the green one. And again, like, keep following it until we get off, and then just keep trying that way. And then the idea here is that we have this py min chance of succeeding to go all the way along the path to y. And in that case, we took at most ty max steps. And if we don't succeed with probability 1 minus py min, we try again. And then this is the kind of sum that we get, that the number of times we have to try it, the probability of trying that many times decreases with the decreases by a factor of 1 minus py each time, but the possible amount of steps we take increases this kind of linear way. And then you can sum up this series and get a band like this on the expected value. Does this make sense? Are there any questions?
Yeah, any tips for how to have done the calculation? Because I worked out the policy. Just
how to do this calculation of the.
Yeah, I was like, any thoughts on, like, okay, once you have a policy, how I could have tried to estimate the expected length of time to reach y?
So do you mean just getting this infinite sum as a bound, or how to sum up that infinite series?
The first one.
How to get this infinite bound?
I guess it's asking for general problem solving tips, but
yeah, so it's it's a good question. So basically, the kind of thing we do is, like, let's say you're trying to flip a coin and get tails. So flip a coin, we get tails, then we're set. Flip a coin again, it's heads, So we didn't succeed. Let's try again. Flip it again. It's heads again. Let's try again. Flip it again. So we get this kind of thing where, the probability or the expected value of the number of steps to success, it's going to be equal to the probability of success, or maybe I should just write it out with that. So it's possible that we succeed in just one step. So in that case, we have the probability of success times 1 time step. It's also possible that we fail on the first time step. So probability fail, which I guess probability fail, assuming is 1 minus the probability of success. And I write, we fail on the first try, but then succeed on the second try. And in this case, we took 2 steps. And then we keep going like this. We fail on the first 2 steps, but then succeed on the third step. And in this case, we took 3 steps, and so on. So that's how we get this kind of infinite series. Does this make sense?
Yes, I understood the argument. Just I guess just the leap to consider a step. So the step here isn't just the obvious one action. It's
Right.
the first time
So
you
this-
stumble up
Yeah,
your planned path. And that was like the leap that made it all just fall into place.
yeah. So that is a good point. That it's important to say this, that we define this T max, because we're basically saying like, no matter where we start from, there's some positive probability of this much of succeeding within this many steps at most. So introducing these is important. So we kind of define our success as having made it in this number of steps all the way to the endpoint. So that is a key thing, that we kind of define the success as being going all the way along this path. That's one instance of success. So yeah, maybe that was the kind of tricky part of it, to realize that by introducing this maximal Tmax, we can still work with that sort of notion of success.
Was it you, Lovkush, who spoke previously about working with minimal paths? Because I think it's probably also possible to make a solution along those lines, but it's maybe a bit more complex.
I mean, I asked, but I mean, you can see from the proof, you just choose any path.
I think you can also have a good policy that tries to go in the right direction. If you define some good notion of distance, like the number of edges of the smallest path toward some goal. And I think you also get a policy that works in this way, but it's a bit more complex to analyze maybe.
Yeah, so yeah, those are good points. Because actually, yeah, as it turns out, and I think someone asked a question about this, maybe Mateusz was asking of like, are we looking at deterministic policies only? And I was saying, so it turns out, so let's say this is our endpoint y that we're trying to get to, then we can actually compute a sort of a function on the other states, which is just basically the expected time, the minimal expected time to y. And then it turns out we can follow a greedy policy, which tries to like take the action that minimizes the minimal expected time for the expected value of the minimal arrival time for the next states. So that way we can even like follow this kind of greedy policy once we have this computed. But of course, computing these is a little bit of work. Or to
Maybe
show
the
that.
proof gets cumbersome because you need first to prove that those things are non-infinite.
Right, yeah. So it is, yeah, I think it is possible to kind of proceed in that way, but it does get a little tricky. So I think this sort of solution bypasses that by just saying, okay, we don't care about getting there very efficiently. We just try something that has a positive chance of getting there, and that's good enough for us, and we just keep trying to do that instead of trying to do something kind of more optimal than that. And that's enough to show that the expected time is finite, which is what we wanted here.
I think even taking the policy, maybe you guys will prove me wrong, but I believe that you can just take the policy that makes uniform random choices always. In which case, you still get a geometric bound on the expected arrival time. And so the exact same thing converges.
Yes.
Because you basically have
the same
you
proof.
then just have a Markov chain.
It's basically the same proof. You just have a much worse probability of success, but it's still non-zero.
Exactly.
Yeah, that's a good approach as well too. Instead of like picking a path for each starting state, another option is just to always randomize your action, and then yeah, that has some positive chance of in a number of steps of arriving at the right spot as well.
The way that I wanted to do the proof that I didn't do because I couldn't figure out how to actually make it work. But I wanted to say, like, okay, we're just going to use the results from stationary distributions of Markov chains, which are fixed points. We'll just transition at random, and we'll just use the stationary distribution results to say, okay, the probability of arriving at this state y must be greater than 0 in the stationary distribution. The thing that I didn't have was any kind of convergence bounds or way to show that this must happen in some way geometrically, directly using the idea of stationary distributions of Markov chains. Does anybody know anything about how to do that? Because to do the result for a Markov chain, you use like a fixed point theorem. I don't know enough about the fixed point results to know which one to use to prove a geometric convergence.
Yeah, so I guess so the fixed point would give you a distribution on the probabilities of being at a certain state given an initial state in the limit of the
But that actually doesn't show that the expectation of ty is finite, right?
Right. Yeah. To get the expected value being finite, you need to do a bit more work. So let's see. But you can probably do something where in the stationary case, the expected time to go from a state x x to y is equal to, like, you take one step and then you get the expected value of the expected value of a new state. And then yeah, I feel like you can probably use this to get a bound on the expected value under this stationary distribution. Because
Wow, cool.
does this equation make sense?
Yes, but I have no idea how you would use it to show that.
Yeah, I mean, it would probably end up being a similar kind of thing where, let's say, you do this for n steps, where n is large enough, and then under n steps you have a positive probability of ending up at y, right? So let's say, yeah, let's p be the probability of end up in y after n steps, and we're assuming n is large enough so that this is positive. Then this is going to be like 1 minus p times, and let's say we look at the maximum of these over x. Let's call this just e. Then this is less or equal than 1 minus p times e. Right. We either with probability p we made it, or with probability 1 minus p we didn't make it, but we're not worse off than we were because we're starting from the worst place. And then putting these together, we get something like p times e has to be less or equal than n, so e is less or equal to n over p.
Wow. Cool. Wow, cool.
So yeah, at the bottom line, it's a pretty similar argument, but
Cool. Yeah, in one idea that Gergely and I had for this course, we were going to do the homework and then do this discussion all together, and then everybody could then redo their homework and resubmit if you want to, which we decided was going to be a bit crazy in several ways, so we decided not to do that. But it would be fun to like redo these homeworks in like the most optimal way, you know, having sort of digested it for a couple of weeks.
right. I guess yeah, we are at time, so feel free to leave if there are any more questions.
I have a small question about the next homework, but maybe you want to take all the questions first.
Yeah, I think we can. You can ask your question.
Yes. So in question 2, there is the definition of an algorithm being better than B with respect to a distribution, and it's written that an inequality should hold for all sample in S in x times y to the power m, but I don't see what m is.
Oh yeah, I guess I meant for any m, so maybe I should have written x times y star.
Okay, yes.
And I think I also forgot to say that. So I think for that question, feel free to assume that y is just 0, 1, so it's a classification problem, and LD is the risk as we defined it in the last lecture. Yeah, I didn't specify that in the question of what the last function is, but yeah, let's just take it to be the error rate.
Okay.
You can probably answer the question in more generality, but I think the spirit of the question is captured in just a special case already. So yeah, feel free to assume that y is just 0 or 1.
Sorry, could you say again what this M is? Okay.
Hmm? Sorry, there is
M is
nothing to repeat.
M is arbitrary, so
So we should replace the M by a star, I guess, in the
yeah, sure.
description.
I'll fix the question. I'll upload a new version after the class.
Thank you.
Any other questions?
I had a small question about the proof we had in the last lecture. Did the proof seem like it highly depended on using accuracy as the loss function?
Mm-hmm.
How important is it? Generally, quite important how you choose the loss function for results, or are you just picking accuracy as a simple choice?
I mean, I would think, the exact results would probably depend on the choice of loss function. And accuracy is pretty natural for the classification case. But you could probably modify that proof for a different loss function and get like a similar bound. So right, because I guess if it's like a classification, you could take like a softmax loss, but it's pretty closely related to the risk or accuracy. I guess the accuracy is kind of a limit of the softmax. Wait, or by softmax I mean like the cross entropy loss that has like a parameter. I think in the limit just gives you the the risk rate.
And another question I had is, how reasonable is the IID assumption? Because in practice, you usually train on like a fixed data set. We don't sort of randomly choose an image at each time step.
Right. Well, I guess, right. I mean, technically you could have like a pool of images and at each time step randomly sample from the pool. So in that case, it would be IID. Just the distribution itself would be determined by the training data set. So that's one way to think about it. But yeah, I guess in practice, you often kind of cycle through your data set instead of picking a sample at random, in which case it's not IID. So yeah, I guess it's a sort of simplifying assumption.
And in practice, the errors from that assumption are just known to be small, or?
I mean, I would think it's so like I would imagine it's in practice. In practice, I think what we imagine is that by cycling through, or like let's say we kind of randomly shuffle the images and then we kind of go through in order after the shuffle. And I think we kind of tend to assume that, okay, there's an underlying sort of true distribution from which all of the images were generated. And then by kind of cycling through our shuffled images, we're close to picking just a kind of random image from the image generating distribution, which I think is probably somewhat far from being true, but it's not like you can do much better. And if instead you took the distribution to be kind of a uniform distribution on the data set that you have, in that case, it's just probably less efficient to sample randomly each time, but because then you're kind of repeating a certain sample a number of times before like seeing all of the samples. So in that case, it's sort of just probably more efficient in terms of actual computation to just look through the images one by one. Although, yeah, I'm actually not sure how this looks in practice. Maybe sometimes there's an advantage of sampling with replacement instead of just cycling through. I haven't done anything practical in a while, so I don't actually know what. I feel like with this kind of thing, you just kind of see what works better and then do that.
So one occasion in practice is if you want to do a bootstrap, and there you are sampling with replacement, and you need to be very careful because your assumptions of IID doesn't work anymore. But I think often in practice, the largest problem is that you don't have the same distribution for the test and for the training. It's much more problematic.
Right. Yeah, if you kind of split your data set into training data set and test data set, even if you do that randomly, they end up being representing a slightly different distribution.
And I guess you haven't seen any theoretical attempts at estimating the cost of the assumption or the errors introduced by these assumptions.
Oh, I'm pretty sure there's some results in theory, but maybe Jean-Marie would know more about this. This seems like a kind of statistics theorem.
So there is a lot of work, and usually it's possible to weaken IID to some exchangeability assumption, for example. And there are some theorems that say that basically exchangeability is not much worse than IID, because there is a theorem that says that exchangeability is kind of the same as IID with a mixture of distributions. So if you that's definitely theorem. And so maybe I don't know exactly in the context of statistical learning, but I think maybe if your set of hypotheses is convex in some way, then it's like you can have mixtures, and then definitely theorem says that exchangeability is no worse than independence, but I'm not sure.
Yeah, I guess definite theorem is an interesting result. Yeah, unfortunately, I don't know much about this. My guess would be that there are some theoretical results, and I think with theory, sometimes what happens is sometimes build out some theory just out of principle because of some philosophy. Like they try to kind of justify certain things, which can be good. Other times, sometimes people kind of retroactively work out some theory where like something was working in practice and someone's like, yeah, why does this thing that people do in practice actually work in theory, or like what's the theoretical reason that it works? And then sometimes in kind of in hindsight, people work out a theoretical result that justifies something that people were already doing in practice. So I think both of those can exist.
I would say that this particular assumption, IID, or things like it, go pretty deep. Like it points to the like this sort of deep assumption. I would say, like within the scientific method, the idea that we actually can ultimately get a bunch of independent data on this external reality. And so it's an assumption that's in there, and yes, you can weaken it in certain ways, but something like that has to be there, or the entire paradigm doesn't work at all, as far as I understand it. Which makes it very interesting, in my opinion. Very interesting to look into.
Yeah, definitely. It's a pretty, yeah.
So another case where you don't have IID-ness is when actually you're looking at something which is slowly evolving with time. So that's a very common occurrence where basically you're kind of in a mixed situation where you mostly have a classification problem, but actually the process or the solution is slowly varying with time. And in practice, that happens quite often.
And I guess another extreme would be like the case of quantum mechanics, which where if you like measure the spin of an electron, then just immediately from measuring it, you already like affected the system enough to, so that's kind of the intersection of what the two of you were pointing, where the system changes and it changes because of observing it. So in that case, the IID assumption does not hold at all. Like if you measure something twice, you actually are guaranteed to get the same result if the measurements are close enough. So that would be sort of the extreme of the failure of the IID assumption.
And do these kind of assumptions affect the alignment strategies in Vanessa's agenda?
Well, if you take like 2 steps back, I think I would say the whole agenda is to sort of question these various assumptions that, and I was thinking of like maybe coming back to this for the last discussion to kind of go through what we've talked about and then see what are the kind of most pernicious looking assumptions. And that one is an interesting project because kind of any assumption could turn out to be pernicious at the end of the day. But yeah, I'd say a lot of the agenda is to like, okay, here's an assumption which is currently kind of taken for granted in the machine learning paradigm, and it's sort of an assumption that underlies the way we train AI today. Like what goes wrong with that assumption as we scale the intelligence, and what can we do to remove that assumption, and what properties remain in the absence of that assumption. So I think there's a lot of those kinds of questions that one can ask, and some of those may be more immediately obviously relevant than others. But yeah, I think any sort of question like that can often turn out to be fruitful for alignment. Yeah, and then your question specifically was about this IID assumption. And for that, I think nothing comes to mind immediately. I think a lot of the work has been focusing on this sort of removing realizability assumptions. Like a lot of the project of embedded agency and combining learning theory with game theory, because those are situations where realizability can be shown to not hold, to never hold. So that's sort of one line of work. And I think a lot of the work has been more focused on reinforcement learning rather than this kind of statistical learning. And this IID assumption was more so for statistical learning. Because if you look at something like Solomonoff induction or ICSI, there you have this thing where the environment actually changes over time. It reacts to what happened so far. So there's not really like an IID assumption in the sense of expecting the environment to always do the same distribution every time you interact with it. So that I feel like that assumption is not so baked into reinforcement learning in the first place. Yeah. Those are some things that came to mind.
So the most similar analog, which is a pretty distant analog of IID, but the way that the same basic paradigm makes its way into Solomonoff induction might be that you assume that the world can be described as something that's fixed. You know, in the case of Solomonoff induction, it's a Turing machine, but it's not the Turing assumption that's important. It's that you say this environment has some fixed nature. And I am able to do some kind of inference process in a way that is outside of that. You assume the world is not interacting with you, looking at your thoughts or your computations as you're doing Solomonoff induction. With those two assumptions, you can do Solomonoff induction. And I would say I'm sort of a distant gesture, but I would say that the reasoning there, like the reason that those assumptions lead to Solomonoff induction, is structurally very similar to the reason that the IID assumption leads to statistical learning, or the analogs of IID, the various weakenings of it. But you have to have something like this to do this kind of learning. You have to have some kind of starting point like this, where you say there is something out there. It has some nature. You can say, okay, it's a probability distribution, and I'm here getting independent samples from it. You can say it's a Turing machine, and I'm here looking at its output and interacting with it. You have to have something like that in order to do this kind of thing.
Yeah, although I think there's like a sort of flip side of this, where even for Solomonoff induction, I think maybe a better way of phrasing is like, here are like some observations. I don't know where they come from. Let me try to model those observations. And if I'm a computer, here are the kind of models that I can have, namely like whatever can be run by a Turing machine programs. So let me like try to pick out the best model I can have given the sort of structural limitations I have as a computer, which is the broadest thing is to just include every possible program, because those are the things that a computer can run. So yeah, that's sort of a rephrasing where you move the assumption, and that's sort of the assumption about hypothesis classes is just that, and it relates to realizability, where if you assume realizability, you're assuming like, okay, the world is the way that I'm assuming it to be. While if you just take a hypothesis class, you're a little bit more reserved of like, these are the hypotheses I'm capable of considering given my limitations. Let me pick out the best of those hypotheses, and then I'm not assuming anything about the what's on the other end of the observations.
Yeah, that's true. But there is this second assumption that the first assumption is that there's this world out there that has some nature. The second assumption is that you have some kind of space in which you can do some kind of inference or induction process separate from the world. And these embedded agency that you're very familiar with critiques are basically looking at, okay, in physics, it doesn't seem like a computer is fundamentally separate from the world. Therefore, let's try taking this assumption away. And there are these, there are ways that you can see that you could do better even as a computer with limited space and computation and whatnot. Better even than AIXI.
So you're saying, or sorry, what was the last claim?
Well, even though AIXI is so powerful in the way that it's defined, still, if you remove this assumption that the environment is not looking at your computations as they proceed, then you can construct certain environments in which AIXI makes suboptimal choices.
Right, you mean like this discipline theoretic paradoxes like Newcomb's.
Yeah.
Right.
Can I ask one other question, if I may?
Sure. Maybe last one and then.
Yep.
Okay.
Are there any results that show if you can reduce reinforcement learning to statistical learning theory somehow? Because the current paradigm does use supervised deep learning to solve reinforcement learning problems. So have there been any?
So the current paradigm uses statistical deep learning to solve reinforcement learning.
For example, like AlphaGo has like deep neural nets that try to learn policies.
Right, but they are reinforcement learning agents. They just have a hypothesis class that's specified by a neural network architecture.
Yeah. But importantly, they've reduced reinforcement learning to supervised learning somehow.
Is that true?
Or in some
I'm not
sense.
sure. I'm not sure what that would mean, because it's still the framework in which it's trained it's a reinforcement learning framework. They get like rewards for like good moves and maybe negative rewards for bad moves. And
yeah, but in some sense, they've reduced the problem to trying to learn the true, let's say, value function.
The true what function?
State value function.
Oh, state value function. Right.
So
yeah.
in practice, that's always what people try to do, to reduce reinforcement learning to statistical learning. But in theory, in statistical learning, you don't have a notion of how much you need to explore. So maybe this is a kind of obstacle to reducing in a theoretical, complete way.
Hmm. All right. Yeah, so that's a good point. So learning state value function, I guess we maybe touched on this briefly for MDPs. So for MDPs, there is a value function, and the optimal policy is just greedy with respect to the value function. But I guess it's not guaranteed to be the case. I mean, for one, it's a bit more complicated for POM-DPs to begin with already, because the state is not observed fully. So even if you have a state-based value function, you don't know what state you're in. And I guess in the case of AlphaGo, the state is fully observed. Like the state is just the state of the Go board. So it's sort of a special case in that way. But I think for more realistic environments, we cannot really assume that we fully observe the state. So I think there's a lot of interesting work there on what to do if your state is not fully observed. And I think that's pretty under researched currently. Actually, like related to what I've been working on in my research is understanding reinforcement learning where you don't observe the states fully. And yeah, it's in that case you cannot just rely on the value function just derived from your observation directly.
Yeah, it does bring up this interesting point that the application areas that have really produced extraordinary results recently are, these two areas. One is playing games with reinforcement learning, and the other is language modeling. And both of them are very much fully observed. You always know the state. Such as it is.
Well, for the language models,
yeah,
there's the second phase of training is a reinforcement learning from human feedback, where arguably you just have the observation of the feedback, but you don't know the state of the human giving that feedback.
Yeah, I would have said in the same way that LLM for me is one of the cases where I would say it's exactly the opposite. It's completely non-observed, because basically if you're trying to guess what comes next in a text, you're trying to work with a system that emits text and which has internal mental states. And so there is a...
True. It's true. I agree, but that is very much not modeled. Like the way that the LLMs are specified is not at all in terms of an unknown state of the other party. Although it's certainly there. It's very interesting to me. It's very interesting to me that they're specified and trained, as just observing a sequence of characters and receiving
it might be
Right.
modeled implicitly inside of the neural networks.
But
it
it's
seems,
not
it's,
baked
yeah,
into the-
exactly.
Right. I need to go now, so I'll stop the recording. But if people want to hang out and continue the conversation, feel free to.